Welcome to our second joint webinar hosted by global mold-based supplier DME and CAD/CAM specialist Cimatron. My name is Ann, and our presenters from DME are Jeff Sarnecki, Regional Sales Director, Dwayne Hicks, Applications Engineer, and Michael Raymond, Director of Engineering. From Cimatron, we have Ralph Piccolo, Director of Sales, and Dan Branch, Technical Support Manager. Let's hear from Jeff Sarnecki.
Hello, everybody. Thank you, Ann. Thanks, Team Cimatron, for inviting us to participate in the second technical webinar. Today, we're talking about cooling. And as everybody knows, cooling is a key part of the injection molding process. Optimal cooling can help decrease cycle time, improve part quality, reduce scrap, and get greater utilization of your assets. Oftentimes, you start off with a mold design and you go through mold flow or a FEA analysis, and you have a perfect idea of how you want to bring the cooling systems into the mold design. And as things get started, ejection, side actions, and lifters are just some examples of where you have to make some changes and improvise. With that, I'd like to introduce Dwayne Hicks. He is our DME design engineer and expert on conformal cooling.
Thank you very much, Jeff. Conformal cooling through additive manufacturing is now becoming a common term in the molding community. And so engineers and designers are beginning to understand that the insert channel configurations can be utilized not only for cooling, but also for heating applications as well. DME has manufactured DMLS inserts with the intention of heating part geometries. These components are mainly used to address higher surface finishes with glass-filled polymers. Typically, these requests have been for connectors and plugs, where smoother surfaces are required for mating faces and usually used with pressurized steam or oil. I have customers tell me that if I can reduce cycle time by even 1 second, they are interested. 1 second may not seem like a big deal, but if we consider the tool is projected to produce 1 million parts a year, well, how much is 1 million seconds? With proper conformal design techniques, we can considerably shave off several seconds off of each runtime. It doesn't take much to save a month of processing time. Hard to reach areas are another reason manufacturers want to use conformal cooling. Standing core features are our second biggest request for design of DMLS. Core features have always been a challenge to cool, and to be able to cool closer to the part surface has made it possible to increase production capabilities. There's also part quality. Part quality issues sometimes become the focus. Many times part quality suffers because of conventional channels cannot cool the part evenly. This can cause a variety of problems, for instance, warping. In some cases, conformal applications can be used to address localized warping conditions. And scrap rates tend to decline just by addressing part quality and those hard to reach areas. It can be very challenging to cool some part surfaces evenly with conventional design techniques. This wire channel model is a good basic example of hard to reach areas. Depending on the size, we could install some cascades or perhaps some baffles, and these methods will obviously help. However, the part surface will tend to be cooler in some areas than others. Conformal methods, being equal distance from the part along the entire length, ensures equal cooling. Anything but perfect cooling does drive up cycle time. Cimatron specifications for the DMLS process. We will share more about this exciting feature later in the webinar. Perfect cooling is nearly impossible to achieve, but there are ways to mitigate loss of precious cycle time. These components were designed with that in mind. I have personally spent time at the press waiting for the sprue to cool, knowing full well the part was ready to eject some time ago. These components create the ability to significantly reduce cycle time by quickly cooling the outside surface of the sprue material, allowing for a faster turnover. Ideally, the object of cooling any part is to cool it evenly. So the more we can reduce the temperature delta, the better the end result. In the example of our sprue bushings, the conventional delta is 44 degrees Fahrenheit, and the conformal with the cooling is about half. In this particular scenario, there was no fancy design. It's just a basic line design, but it helped because they were using this insert for gating, and there was no way to really get cooling conventionally into it, such as a baffle. Collapsible cores are another big seller, and they are conventionally cooled, typically with baffles or a spiral baffle. But just by adding conformal to this, we can reduce the cooling time for these cores by an average of about 15%. Even with minimal conformal techniques, we can still drop it enough to make a difference, even if it's only a half a second or 1 second. These are becoming very popular with DME and with the manufacturing community. They are slightly compact, but they're for bigger drops. They're a little less than 100 millimeters in diameter and 100 millimeters tall, which is about 4 inches. These slim gate bushings are designed to eliminate drooling and blushing on the part surface and are great for clear ends applications. They work by cooling and containing the heat around the gate area with minimal stress to the heating elements. They are relatively universal and provide off-the-shelf as blanks with the outer details complete, but stock full in the tip area. This makes it possible to add the detail of the tip for whatever drop configuration our customer may require. Coming soon are compact inserts. And this is going to be very helpful for multiple daisy chain scenarios. They are under 3 inches in diameter and about 3 inches tall and provide the same function as our slim gates. And this is very exciting for a lot of people. Our DME's cooling delivery system for lifters. In the past, we would design these to customer specifications for existing designs. Now it will be possible to apply these components during the design phase, and they are also interchangeable with trunnion applications. Jeff, would you like to give us a recap on the AccuLine lifter system?
Sure. So just to recap, the AccuLine lifter system has been in the market now for a little while. And essentially, we're offering a system here that can auto-align or auto-tune itself as the manufacturing process or the build process is going on with the production of the injection mold. We provide the D2 slide shoe that has a wired ball slot. It's slightly oversized. When you add in the ball retainer in conjunction with the dovetail right there within the ejector housing, you get two areas of what we call auto alignment. Depending if you stick with a round rod as you make or produce a custom lifter head, we offer a grommet that allows the head of the lifter to float. So through the injection molding process, as you have thermal expansion, or even in the build process, if you miss a tolerance, this system will auto align and prevent itself from catastrophic failure. Two types, as I'd mentioned, we have the round lifter rods, which in the near future will be able to be integrated with our cooling rod technology. We also offer a blade style that does lend itself to a lot of different large and small applications. As you can see here in the diagram, we offer some carbide rollers that help through long ejector strokes with tricky larger type applications. Getting into the cooling part of this again, baffles are very commonly used to reroute water through standing cores and cavities. The most popular types are your brass. You have your brass flat, your brass spiral, as you can see in the illustration there. Very common application to reroute water with these types of products. Utilizing these products, however, you're mostly going to get laminar type flow. You will get some turbulent water flow in the very beginning of the process or of the flow, but ultimately, unless you make some changes, you're going to maintain or just exist with laminar type flow. DME a little while ago did introduce the plastic baffle. We got a patented design here. We have some features that help provide consistent tubular flow as these waters reach standing cores and standing cavities. This will definitely help you reduce your cycle time, reduce energy cost, maintain a lower temperature delta, eliminate scraps, and it's also very easy to install. Being that they're plastics, it is a polyphthalate material that we use in the radiator application, so it can withstand higher heats. But as you can see in the diagram, it's got different slots or cut points every half inch. But even if it's in a non-standard size, you can use a pair of side cutters and cut these down to length very easily. In addition, they come pre-wrapped with a Teflon tape to prevent any type of leaking. Now this video here, it's a bit older. This is available at dme.net, but it gives you some examples where if things aren't installed correctly in a spiral or flat brass baffle, you can get under pressure, you can get the water to blow by or air to blow by, not allowing the water to actually reach, the part of the geometry that needs to be cooled. The plastic baffle there in the center is showing you a consistent turbulent flow through the cooling process. In addition, the way that these things are made, we have some fins that are on the side, so they can be installed slightly undersized to avoid blow-by. Then after the event, in our sessions, we're going to be talking about our conformal cooling. As many people know, conformal cooling inserts can pose some issues and challenges with the water lines themselves getting clogged. And for that, we've introduced our new cooling care unit to help maintain and provide optimal cooling throughout the molding cycle.
All right, at this time, we're pausing to answer some of your questions, and just post them in the chat window, and we will respond as they come in.
So one question that I do see is when the conformal cooling sprue bushing, maybe Dwayne, you can address this one. When you get a situation where you actually have two parts, being that the sprue itself can be considered a part, as well as the part that's actually being molded in the process. What kind of cycle time can we expect to see utilizing one of these components?
Well, it's going to be standard. Depends upon how big the sprue is, how long the sprue is, how much material's in the sprue. But you could definitely, for let's say 4 inches, you could definitely shave off 5 or 6 seconds, easy.
At this time, we will turn our attention to Cimatron, and Dan Branch is next.
Thanks, Ann, and appreciate everybody joining us today. Quickly though, for anyone who may not be very familiar with Cimatron, we're a fully integrated CAD and CAM software solution. Cimatron is purpose-built for the design and manufacture of molds, dies, fixtures, and especially complex tooling like automotive work. That's really what we do best, and you'll see that illustrated in the various functions I want to show you today. Yeah, today's webinar really is all about mold cooling, and DME just highlighted a few new components for us. So next, I want to show some design functionality, but a few points I can make here first. Now, as we've said, mold cooling is typically the longest part of the molding cycle. So anything that pays off, or excuse me, anything that really improves cooling is going to pay off immediately. And we should also know that it's probably going to mean a better quality molded part too. Cooling system design needs to be well thought out, but it should be easy to manage, and it also needs to rely on those standard components that are going to work with the press and the facility, and also any opportunity to incorporate some conformal cooling should be considered whenever possible. I'm going to switch over to Cimatron now so we can take a look at some mold design. And like in the first webinar of this series, let's start by just looking at a plastic part to be molded. This time it's a bit of a cover with some deeper walls and features. And our quick split function has already helped me define the main direction of draw here. And then it also singled out these surfaces in green as an area that has to be pulled over to the side. Now, after we did all that sorting, some shut-off surfaces were developed. Cimatron has a well-earned reputation as a great surface modeler, so this all came together really quite easily. Now, if I check the draft status of the part, which I can do while still in the split mode, I do see that everything seems to be arranged okay, And most importantly, there are no overlooked undercut features that would be showing up in red here. So if we're good there, we can move over to mold design. Let's take a look at the one I've been working on here. It's going to be a single cavity on individual cavity blocks, so it's something that fits just fine in a standard DME mold base. And we did look at mold base creation in our last webinar, so I don't want to really repeat what's already been seen. But if I did want to edit the mold base, I would return to this same screen. Currently, I've got an A-series base picked out, but there were plenty of options there, standard sizes, plate thicknesses that would accommodate this part. About the only thing I did do was I chose to delete the standard sprue bushing. The center holes in this mold are going to be offset anyway. Plus, we can look at adding the first of those new DME parts, a sprue bushing that has cooling channels in it. The Cimatron has some nice dedicated screens for adding mold components. These help you find the right part and provide automated rules for placing it. One category is for injection components, and it's in here that I find the DME conformal cooled sprue bushings. And there are a lot of sizes to that part, but I can filter some off. For example, I only want to see the bushings with a 3/4 inch radius. And I'll need the longest one available to reach through this deep cavity block. Cimatron, of course, really excels at simplifying the placement options for mold components. I already have a reference point on the mold base, so I can drop it in, and then it's easy to rotate the bushing around. So in this case, I kind of want those water pipes to be shorter. And then I also want to choose an option here to cut with this part. Doing a cut means that I want the part being added to make its own correct pocket. So in this case, it creates the hole in the cavity for me. And then there is a little extra material on these sprue bushings so that you can modify the end, like to chop it off even with parting line. And I'll need to add a runner too. But we're going to move ahead, just look at the part. If I do a simple 3D section, it lets me actually see the internal cooling lines that these sprue bushings have. Like all Cimatron catalogs, this part is parametric, so these channels are going to adapt to whatever length bushing you happen to select. And as you can see, in this design, the sprue is a pretty thick piece of plastic. Like we were mentioning a second ago, cooling the sprue bushing like this is really going to remove a lot of heat that otherwise might be the holdup for ejecting the part. Now, being that the main focus of today's webinar is mold cooling, next I want to talk about regular drilled water lines for a minute. Because we often think of these as circuits, kind of with an in and an out, Cimatron has a function that thinks in the exact same way. To illustrate that, I'll define a plane and just keep creating a water circuit. As I do, you can see the system opened up a special part. It's a cooling part, and I've already got one circuit going here. I want to add another at a different depth, and I'm completely free to just sketch out what other pathway I'm thinking of. The edges of the block or existing cooling holes can provide references that help me position these new lines. I do have some idea of the circuit I want at this level, so I'll draw it out here. Keeping in mind, of course, that drilled lines do have to start from one side of the block. And then probably going to add some nominal dimensions on the lines of this new circuit too. Having a dimension means I can parametrically edit the position of a water line later on if it needs to move, which of course they often do. So a cooling object function then is going to create the pipes that follow this sketch. And it has several options like the channel size or the drill overlap. And another cool thing it can do is a quick analysis for any water collision issues. That works by intersecting the cooling lines with the cavity geometry. In red here, I'm being shown where the lines break out of the block, and hopefully nothing else. But I might see some more once I apply an offset to the lines. This adds a safety distance on top of the channel diameter and again checks for problems. So at a 1/4 inch, I'm not seeing any other collision, but if I move that up to 3/8, now I do see a pretty big area of part geometry that touches. So what that's telling me is if 3/8 is my desired safety distance, I do have to move this end water line farther away. About the only option I'm not going to choose in this function is to cut the lines in the block, but that's only because I might not be done designing the water. And when I am done, there's a function that'll just cut the entire cooling part into all of the blocks that it crosses. That's this cooling cut function, and it has a nice table for full control over whatever components I need to cut the water in. So with a good water circuit in place, the next thing to do is add some standard components that are needed to direct the flow. To add some plugs, I'm going to go back to the many smart mold design menus in Cimatron and get directed right to components for cooling design. I won't even have to choose a size because the system rule knows which plug to use based on the drilled size of the cooling line being selected. So in one step, I can just drop some pipe plugs on any line that needs one. I'll get the new component added to the mold design, but also to the bill of materials. Plus, these plugs are going to cut their own pipe threaded holes in the cavity block. Other components are just as easy to add. Finishing up here, for example, we need some extension plugs to get water over to the cavity. And these auto size as well, but I do want to choose the connector style I want from the many options. And the nature of extension plugs, of course, is that you order them long and then you cut them down. So I'm just going to round these off to a nominal size that works for the thickness of the mold plate in this area. Yeah, that looks good. I need to add a few more to get over to the conformal cooled sprue bushing, but what I want to do is keep moving on here. Another nice Cimatron function for cooling design. It's a tool that can check out the water circuit routing. That's called Analyze Cooling. It's a function we build it to find potential problems in complex water circuits like parallel streams or maybe an inlet that doesn't have an outlet. And one of the things it does is it understands what types of components are in use in the design. So by checking that first, here it locates all of those previously placed plugs, and then it colors the areas of the channels that would be considered a dead end. And from there, I run the actual analysis, which follows the water inlet around until it reaches an outlet. Now, a collision or a routing problem would color the line yellow, but here I only see the color for running water, and that assures me that I don't have any geometrical problems going on so far. So we blasted through a bit of design stuff there. Seems like a good time to pause for any questions you might have at this point. Ann?
Yes, let's check to see. Please post your questions in the chat window and we will respond.
Hey, Dan, one question that I often get is about the mold component catalogs. You know, is that something that the user has to create? Are they already in the system? How does that all work?
They're already in the system. We're constantly updating all the catalogs that Cimatron supplies. And we have this nice partnership going with DME, so we've been focusing on those. They're on a cloud server. So as a user, when you're dealing with catalogs that you need, you can go to that server, download what you need, or check for updates too, because we're constantly adding those as well.
And those catalog components, they include the cutting objects as well?
That's right, because they're built for Cimatron. Everything's custom. They're parametrically driven parts, and parts for Cimatron are all going to have a cutting object to put in the right pockets, yes.
Okay, good, thanks.
Let's move forward with the presentation.
Okay. Well, next up, I want to talk about getting those cooling channels for free, just by placing the cooling components that you need anyway. And a good example of when to use that method of design is when placing baffles. So let's drop in a few of these new DME plastic baffles. The function I'm referring to is called adding a cooling item with channel. And it starts off in this familiar way by selecting the component from the catalog. In this case, I'd like 4 baffles, 1 in each of the taller sections that this core block has. And the baffles themselves preview at a default length, but notice on the screen how many options this function has. Each one of them is a way to automatically control the size or length of the cooling channel. And what usually works best for baffles is to set the length control at what's called maximum length. What that's going to do, if you notice the green tube around each baffle, that's the hole, the drilled hole for the baffle. But really, I'm more interested in the pink colored tube around that. This is the safety envelope that each baffle is actually adjusting to. And it's controlled right here. So if I want to change or check the safety distance, I only need to type in a new value. The baffles themselves in gray, I know they're still showing too long, but really that's just a preview. I'm looking at the tubes. I trust the function to be correct, so I've already hit approve here based on those channels, and each catalog baffle is now going to be trimmed off appropriately to fit the water channel that it sits in. So I know each of these baffle channels is safe in every direction to the core geometry. And next, I just need to add some connecting lines, either by adding another component with a channel like we did, or by using that circuit method that we started with. But we'll move on. I'm hoping that most of you have already had a chance to watch our first Cimatron DME webinar. In that one, we discussed several new types of mold components, including those AccuAlign lifters Jeff was showing. And it is an excellent system. And if you notice, when using the round lifter rods, you can now get an internal pipe to carry water up into the lifter head. And that's something I would want in this job, as the lifter is relatively large. I'm sure the plastic part would benefit from cooling it. And I could design a few conventional cooling lines into the lifter, but it does have a lot of molding surface, and that limits the areas I can drill into. So the ideal way to get the best cooling throughout this lifter is going to really be with conformal cooling. And I know a lot has been written about conformal cooling in the last few years. I think the benefits of it are really getting well known. Conformal can get water passageways much closer to the part surface. It can get them into small areas that drilled water lines just can't reach. And yeah, it does mean that the component will have to be 3D printed. But we've got partners now, even like DME, that can provide that surface. So it's really not such a limiting factor. And if you haven't seen the quality of a 3D printed metal part lately, I think you'd be surprised at just how dense and how pure they actually are. But what about designing the conformal channel? Just how is it done? Cimatron has a function to show exactly that. I want to show some options here. Unlike the cooling circuit function, the conformal tool allows for a variety of waterline shapes. And these are all proven cross sections that provide a lot of surface contact with the steel to remove the heat. And the other important feature of shapes like this is they minimize the downward facing area. When you're 3D printing, downward facing areas need support. And creating support structures inside water channels is not really a good idea, so we want to avoid that if possible. Now, the system wants you to define the path, and you could spend a lot of time thinking about it, drawing a bunch of very specific curves through a part. But let me show you our cool idea to make that easier. I want the system to create a new lifter body, one that has every face offset inward from the actual steel. So theoretically, if I plot a course across this new body, the cooling channel is going to be at a constant depth from the skin of the lifter, the actual surface, to promote good heat transfer. So here I'm actually going to give it a little more realistic offset. We need some room. And then just start picking points that will lay out a conformal cooling pathway. At every point along the path, the section is previewed, and I have that dialog available. So that provides for a huge amount of adjustability in the channel size and the channel shape. You can even turn on a parameter to continuously twist the channel. So that provides even more variety in turbulent water flow. I'll preview it, and that would be the proposed conformal cooling channel. And I can actually have the same function while I'm designing, do some analysis on the channel. One of the checks I can run is an overhang analysis. I mentioned downward facing surfaces are not good, but as we can kind of assume, they're unavoidable. So what this does is it measures the ramp up to those downward faces. The printing machines can make the next layer of material okay if the angle is slight enough. So here the triangle section is a good one to use, and I don't see any problem at 45 degrees. But if I change that ramp up angle to 60 degrees, then I do get some yellow areas, and those would not satisfy the condition. So maybe I make some adjustments to the channel or to the twist. And then next here, we're moving on. It's a safety distance analysis. So as you saw, I plotted the path just loosely on an offset model. This is going to check and verify that the actual channel falls within that optimum distance from the part. And I want to see green. Anything in red would indicate an area that is too close to the part. Now, besides the analysis result, this same option can actually automatically fix the problems. Not just the areas that are too close, but also any that might be too far away. And it's really doing an amazing job. Some corners tighten up closer to the part. But I also have one section here that illustrates a new problem. To clear that red area, the system bent the channel. And it was between those points so sharply that the channel would fold over on itself. But that's the thing about conformal cooling channels. There are no manufacturing limitations. Every point in the path is easily adjustable. So here I'm just dragging and smoothing out the problem area. Cimatron makes this really easy, and it eliminates the sharp bend. So this preview confirms that I've fixed my problem. And the result is a pretty good pathway to get water actually from that lifter rod through the part and then over to the rod again. I mean, quite clearly, you can design a conformal water channel however you want to. But this is a task where automation can help. So we did take this idea one step farther. Rather than having to plot your own pathways, you can ask the system to automatically develop the best route through the part. The automatic conformal function wants to know what faces of the part are in need of cooling. And it can seek that out based on a criteria, maybe like color. In order to chart out a good path, I'll establish a few parameters, like what the basic channel diameter will be and how far away to stay from the part surfaces. And here there's also a vector control, and that has influence over whether the channels that it's going to make for you will be primarily horizontal or vertical. Now, selecting where the cooling channel starts and ends isn't a required step, but in this case with the lifter, I know where the water is coming up from. So those are inputs I want to provide as well here. So based on those parameters, I've been given a blue curve, and that is the path that I could then choose in conformal cooling to lay a channel on. But now that I think about it, the lifter is a relatively small component. Maybe we could just run cooling throughout the whole thing. So I'm going to go back and edit this and make some adjustments. One of them is to consider all of the faces of the part. And then maybe allow a bit more room between the channels too. And I really like this result. If you look at it, it's stayed clear of the screw hole. It stayed clear of all the other pockets that the thing has. And I'll just go back to the same conformal cooling function with a nice safety checks and put the actual channel onto the automatic pathway. This time we're just going with a round shape. I do have a ton of options at each portion of the curve, but I think this will probably do just fine. I'm even going to skip the preview of it and go ahead and cut the channel right into the lifter part. So here is the finished lifter. And that crazy conformal channel in there starts and ends in coordination with the lifter rod. So it's going to work great with the other standard DME components that are already placed in the job. Before I end today, we're moving through this kind of quick, but I do have one time for another addition to the mold design. given all of the water channels in this tool, I may want a water manifold to help with the plumbing. And those are a very recent addition to the DME metric mold catalog. There are 3 styles here. Each one of them has a very large number of options, size of the part, number of ports. So drop it here, and man, there is another standard mold component easily dropped in place. So that manifold joins all of the other components on the mold and running bill of materials. Once I wrap up the design, I'm going to export this off the DME, and I'll have all my parts ready for the shop floor. And that's it. That's our short demonstration on the features and benefits of designing mold cooling with Cimatron, along with interactive standard catalog parts from DME. This is just a portion of what we can show you about our integrated CAD and CAM for tooling. So let Cimatron help boost your productivity and provide a competitive edge for your mold builds. Thanks for the time. Let's pause to see what other questions we may have.
Thanks, Dan. Remember to post questions in the chat and we will respond.
Hey Dan, one question on that automatic conformal cooling channel. If you had ejector pins in place there, it would take those into consideration and stay away from those?
Yeah, it absolutely does. It stays away from everything. It deals with the volume of the surfaces you picked. It knows how far to stay away from itself, even, Ralph. So as it's bending around, it's using a very smart algorithm to give you the best in and out and channel that it can. It's pretty cool.
Wow, that's nice.
Yeah.
The other thing is on the bill of materials there now, when you're placing like the DME mold component there, it's going to have the DME order number?
Absolutely. Yeah, a catalog part, of course, has a number of sizes within it, but each size knows that it has a part number that is assigned to that size. Yeah, the bill of materials works in a very automated way. And we'll edit and change. If we change the size, and the BOM knows that too.
Okay, thanks. One last thing on the everybody questions the conformal cooling channels and what happens when they get plugged up and you have to clean them out. What I've seen out there, and I'll put a little plug in for DME here, they have this cooling care unit that basically cleans out those channels, and a few of my customers, our customers, have those, and they're amazed at what it does. So if you guys have a few minutes, go after this, head over to the DME session, and they're going to show some good stuff on the cooling care and cleaning out all those channels.
All right, well, it looks like we are able to move forward by closing. So I'd like to thank you and have a wonderful day.